Alrighty. Hey AP Chemists, this is going to be a brief video on looking at the composition of mixtures. In class we mentioned that if I have a mixture of some samples, I could figure out through stoichiometry the percentage of that substance in the mixture. If I know the mass of the substance and I know the mass of the total sample, if I divide those two, multiply by 100, I'll get my percentage of substance. The big thing here though is usually the way that we get our mass of our substance is by doing some form of stoichiometry. So in class we had this problem. We had the aluminum metal, it reacted with air, and it formed a thin corrosion-resistant coating of aluminum oxide, according to this following equation. We ended up balancing in class, so I skipped that here. For every 4 moles of aluminum, I have 3 moles of oxygen, and I get 2 moles of aluminum oxide. And I drew some pictures here, so our balancing is good. A block of aluminum having a mass of 120.32 grams was left out, and some of the aluminum was oxidized to aluminum oxide. So now I have a mixture of aluminum and aluminum oxide. I don't know how much aluminum, I don't know how much aluminum oxide yet, but I could figure out how much oxygen was added through subtraction. So that gets us to our mixture of aluminum and aluminum oxide is 120.91 grams, as mentioned. And so now I balance it. What mass of oxygen was in the sample? Well, if I know the total mass of my aluminum and aluminum oxide, and I subtract it from just the mass of aluminum, the only difference is going to be the O2 that was added. So I could do my 120.91 grams subtracted by my 120.32 grams, and I will get 0.59 grams of O2 that was added. Now that I could do that, I could start thinking about what's the mass of aluminum oxide in my compound. Well, we're going to have to use stoichiometry. And again, if you're struggling to see the math that I'm about to do here, look back at the videos for summer work on how to do stoichiometry. So what mass of aluminum oxide? Well, I know that the molar mass of O2 is 32 grams per mole. The molar mass of aluminum oxide is 101.95. And then for every 3 moles of O2 that are reacted, 2 moles of aluminum oxide will form. That's going to help me do the stoichiometry. So I'm going to start with my 0.59 grams of O2. I'm going to convert that to moles by dividing by its molar mass here. Then, now that I have moles of oxygen, I could do my little stoichiometry, mole ratio here. For every 2 moles of aluminum oxide formed, 3 moles of that oxygen is used. And then this is going to leave me with my moles of aluminum oxide that I could then multiply by its molar mass to get the grams of aluminum oxide that are present. And if you do all this math, you should get approximately 1.25 grams of aluminum oxide. Boom. Which leaves us to the last part here that we did in class. What is the mass percent of aluminum oxide in that aluminum and aluminum oxide mixture? Well, I'll need the mass of aluminum oxide that I now have is 1.25 grams. I'll need the mass of the mixture, which I know is 120.91 grams. If I divide those two, part over whole, and multiply by 100, that'll give you my percentage. So I'm going to do that. 1.25 grams of the aluminum oxide divided by the 120.91 grams of the aluminum oxide mixture times 100, and you should get approximately 1%, 1.4% to be exact. Okay? So we did that question in class. For your homework, I wanted you to start looking at the we do and the you do. And I'm going to do that for the next couple of minutes now. So let's look at the next question here. The main component of eggshells is the compound calcium carbonate, CaCO3. If you react the eggshells with acetic acid from vinegar, the following reaction will take place. So I got my eggshells, I react it with acetic acid, and I get water, carbon dioxide, that is a gas that comes out, and calcium acetate. If 4.421 grams of carbon dioxide was produced from 10.57 grams of eggshells, what percentage of the mass of the eggshells was calcium carbonate? So now I have some information here. I have an amount of carbon dioxide that came out, and I have a total mass of eggshells that we got here. I looked up and have some information for you here. The molar mass of CO2 is 44 grams per mole. The molar mass of calcium carbonate is 100.1. And what's so nice of us here to have, for every 1 mole of calcium carbonate, 1 mole of CO2 will be produced. So now I can start doing my stoichiometry. I could go from my grams of CO2 to my grams of CaCO3 using stoich, just like we did up here in letter C. So I have 4.421 grams of CO2. I'm going to convert those grams to moles. 1 mole of CO2 for every 44 grams of CO2. Then, lovely, I have a 1-to-1 mole ratio. So 1 mole of CaCO3 react with 1 mole of CO2. And then I can convert that right over to grams. There are going to be 100.1 grams of calcium carbonate for every 1 mole of that calcium carbonate. If I do this math, I will arrive at how many grams of calcium carbonate are in my eggs. Do that times 100.1. I get 10.06 grams of calcium carbonate in the eggs. But we're not done here. It wants the percentage of calcium carbonate in the eggs. Well, I'm going to need to do some math here. To get that percentage of calcium carbonate, I'll need the mass of the calcium carbonate, which I got, divided by the mass of the eggs, times 100. And so that becomes 10.06 grams of calcium carbonate, divided by 10.57 grams of the eggs, times 100, and I get 95.2% calcium carbonate. Done. All right. So now I'm going to start getting you ready for the you-do here. And I'm going to give you some hints to get you to do this on your own. For this you-do, it says we have a 15-gram sample of sodium hydrogen carbonate, and I gave you its molar mass as 84 grams right here. And it was contaminated with an impurity. In order to determine that purity, it's heated to decompose the material, according to the following reaction. It looks like for every 2 moles of sodium bicarbonate, or sodium hydrogen carbonate, I will get 1 mole of sodium carbonate. If 6.35 grams of sodium carbonate were recovered, what percentage by mass of the sample was sodium hydrogen carbonate? So this is just like the we do question from before. We're going to start with the 6.35 grams of the sodium carbonate. You're going to want to convert that to moles. For every 1 mole of sodium carbonate, there is, I gave you the molar mass here is 105.99 grams. Then I'm going to start going through mole ratio here. 2 moles of sodium bicarbonate for every 1 mole of sodium carbonate reacts. And then finally, the last step is going to get me to go from that mole ratio to my grams of sodium carbonate. 84 grams of the sodium hydrogen carbonate or sodium bicarbonate. That vocabulary is the same for every 1 mole of sodium hydrogen carbonate. This is going to give me my mass of sodium hydrogen carbonate. I'm going to let you do that math. And then if I want my percentage, it's going to be my mass of the sodium bicarbonate divided by the total mass, which is the 15 grams, times 100. I'm going to leave you to do the rest of that percentage to get the answer. So you're going to do the rest of the you do. I'm going to set us up for numbers 2 and 3 and end my video here. I put some little notes here. A sample of brass weighing 2.03 grams was analyzed. Brass is an alloy, so you might see the word or hear the word alloy, composed of copper and zinc. The zinc in the alloy reacted with 35.123 grams of hydrochloric acid in excess, according to the following balanced equation. So I have zinc, I reacted with hydrochloric acid, and I put this highlight hydrogen gas is going to bubble out. It's a gas that leaves. After all the zinc reacted, the mass of the remaining hydrochloric acid solution and unreacted brass weighed 37.107 grams. Assuming the mass of the unreacted alloy and hydrochloric acid was 37.153, that's this business. And I know this kind of says like remaining or unreacted, but I'm saying the original. The mass of the original unreacted alloy is 37.153 grams. What is the mass of hydrogen gas that was produced? Well, to get a little picture here, if I have my beaker and I have like my alloy in here, and then I have my beaker with some hydrochloric acid and my alloy after with some hydrogen gas that kind of bubbled out, my mass is actually going to decrease, and that decrease in mass is going to be due to the hydrogen. So the way that I want to solve the mass of the hydrogen that bubbled out is I need the mass of the unreacted minus the mass of the reacted or remaining. So that'll be my 37.153 grams minus the mass of the leftover remaining 37.107 grams, and you should get about 0.43, something like that. 37.153 minus 37.107. You get about 0.046 grams of H2 that popped out. Oops, I didn't mean to erase that. Go back. Okay. So with this information now, and knowing that the molar mass of H2 is 2 grams per mole, I'd like you to try and answer B and C on your own. What mass of zinc reacted? Well, the molar mass of H2 is 2 grams per mole. The molar mass of zinc is 65.39 grams per mole. And for every 1 mole of zinc, there's 1 mole of hydrogen. This makes our stoichiometry a little bit easier. If I know how many moles of hydrogen there is, that's how many moles of zinc there are, and then I can convert that to grams. And then finally, if I want the percentage of zinc by mass in the alloy, I would take my mass of my zinc that I get in part B, divided by the mass of the brass, which is actually 2.03 grams, multiplied by 100. If you want to check your answer, you should get about 74% for part C here of zinc in the alloy. I'm going to have you check your answer there. And then finally, the last you do question that I wanted you to try and do on your own is number 3 here. This says a sample of sodium bromide has a mass percentage of sodium, which is 22.34%. Getting the percentage of each element in a compound is prior knowledge from chapter 3. If the sample of sodium bromide were contaminated with sodium chloride, would the mass percentage of the sodium be higher, lower? It justify. Letter B is also a similar one. If it was contaminated with sodium iodide, would the mass percentage be higher and lower? Here's my little hint here for you that I'm going to have you use as kind of like a reasoning or a claim or evidence here. The percentage of sodium and sodium chloride here is actually 40% compared to the percentage of sodium and sodium bromide, 22.34%. And the percentage of sodium and sodium iodide is 15%. So I'm going to say higher, lower. This is my hint to you. Use these percentages now to then answer this question. Would you expect this impurity to make the sodium percentage higher or lower in each of these cases? And explain why using this information here. Alrighty, that is the end of us working through this video with the I do, we do, you do. It is my expectation that you try and answer at least the rest of the you do 1, 2, and 3 on your own, and we will go over this in class. If you have any questions or concerns, you could always reach out to me.